so today we're going to be looking at section 1.17. Section 1.17, which is on changing coordinates in double and triple integrals. Let me show you some triple integrals today. Integrals of functions of three variables. Just quick announcements before we start. I am continuing to update the solutions on Moodle, so you can now find all the solutions up to where we are, up to exercises 1.6 up there, so you can use those in your work. So, as with a lot of these things, before we introduce something new in multivariable calculus, we look back to a familiar equivalent thing in one variable calculus. Okay, so this is where you probably know it as integration by substitution. Okay? You think back to integrals of a function of a single variable. On the left here, you've got standard kind of thing, integral of a function of x dx, and on the right-hand side, well, you've got an equivalent integral. But we've now changed the representation, so no longer is x the variable, the argument of the function and the variable of integration. On the right-hand side, you've performed a substitution, so you've replaced x with the function t. So you evaluate f of x of t. So the integrand, the thing you're integrating now, would now, if you evaluated this out with a particular example, would now be a function of t. And you also, but you don't just change the x to t, you also have to have this bit which multiplies the new differential t, which is the derivative dx dt of the transformation. Okay? So to transform the integral to one involving the variable t, you have to replace x everywhere by what it is in terms of t. So that's replacing the x with x of t inside of f. But then you also have to make an adjustment to the differential, okay? And that adjustment is dx dt. Okay? So what we want to describe is a way to do a similar thing for functions of, let's just look at two variables in the first instance, okay? But it generalizes to functions of more than two variables. So here in equation 189 here on the left-hand side, we've got a double integral. Okay, these are the kind of things we've been doing in the last few lectures. The double integral of a function f over a region R in the plane. And we're integrating with respect to x and y. And the function we're integrating is described in terms of x and y. Now, if we, for various reasons which I'll come to in a moment, but if we want to change the integral to instead represent it in terms of a new coordinate system, so not the old Cartesian coordinate system, x and y, but for various reasons it might be better to transform into a new coordinate system. So we'd like to express the same integral in terms of the new coordinate system. Okay. Well, we're still, so this, now we'd be looking at the right-hand side of the equation 189. We're still integrating over the same region R in the plane. But now we don't have a function of x and y, now it becomes a function of s and t. Okay? So changing to a new coordinate system s and t, we would know how to express x in terms of s and t and y in terms of s and t. Then we have the new pair of differentials, ds dt, but then there's also this adjustment factor. So this is the Jacobian determinant, which we met back in the section on the chain rule. So if you look back to the section on the chain rule, which is all the way back in page 19, no, even earlier than that. Didn't think it was back this far. Okay, so this is back on page 15. When we did the chain rule for functions of two variables, we introduced this object called the Jacobian. This Jacobian is the matrix of partial derivatives of the transformation. So here we have the Jacobian at the bottom here from of the transformation from the Cartesian coordinates x, y to some new coordinate system, st. So it's a matrix of partial derivatives. We have dx ds, dx dt on the first row, and dy ds, dy dt on the second row. Now this is alternatively called the Jacobian matrix, and the determinant of it is called the Jacobian determinant. Sometimes the term Jacobian is a bit ambiguous. They could be talking about the matrix or the determinant by just using the word Jacobian. Now why might you... So when we transform the integral, so just come back to where we were. Sorry, when we transform the integral, the new differential then is, so we replace the dx dy part by, sorry, I'm still scrolling here. We replace the dx dy part in the original integral by the absolute value of the Jacobian times the new pair of differentials, ds dt. So this term here is actually the absolute value of the Jacobian determinant. Now, why might you want to change coordinates? Well, you might want to change coordinates for two main reasons. First of all, the region you're integrating over might be more easily described in the new coordinate system. Okay? We'll see this in an example coming up shortly. And secondly, the function you're integrating might itself become simpler once you make the transformation, and might become possible, might become a doable integral, an integral that you actually can carry out. Okay, so let's have a look at this first example, example 1.21. Then I'll show you some examples of functions of more than two variables, and we'll explain a little bit more about the meaning of the Jacobian determinant. So in this example here, example 121. We're asked to integrate this function 1 over x squared plus y squared, integrated with respect to x and y over this region R here. And this is a part of the annulus. So the annulus, an annulus is a region between two circles, or two spheres, if step up higher dimensions, I guess. So this shaded region R is a quarter of the annulus between the circles of radius A and B. Now, with both the region we've been asked to integrate over and the function we're asked to integrate, they're both very circular. Okay, so the region is an area between two circles, so that's obviously very circular. And the function you're asked to integrate, 1 over x squared plus y squared, well, the sum of squares, x squared plus y squared, is of course equal to the square of the radius. Okay, so the integrand is kind of very circular as well, the function you're asked to integrate. Now, integrating that expression 1 over x squared plus y squared with respect to x or y directly, well, we can't really do it directly. And in order to carry out that integral, we would use, in general, a trigonometric substitution. It becomes a lot easier to integrate it if it's just the function 1 over r squared, because that's already simpler. It only depends on one variable. So this is how the transformation goes. It's worked out down here. So, well, the function 1 over x squared plus y squared, as I said, that's equal to 1 over r squared. The absolute value of the Jacobian of the transformation from Cartesian coordinates to polar coordinates, well, we already worked that out back when we looked at Jacobians before. So that was equal to r. Okay? So the new differential now is r dr d theta. Okay? So that simplifies the function you're integrating. It now becomes 1 over r. Yeah. And that's going to be, we're going to be able to integrate that, because that will integrate to a logarithm. Then we need our limits of integration. Okay? Now you always work from the outside in, remember? So the d theta integral is the outside integral. So you ask yourself, well, between what polar angles is that region R? Okay, so theta, remember, is the angle between the radius and the positive direction of the x-axis. So all these points in here from an angle of 0, these points down on the x-axis, to an angle of pi over 4, these points here, halfway, and then up to pi over 2, all these points here. Okay? So you need to vary the angle theta between 0 and pi over 2, you decide on the limits of the outer integral first, and then you step into the inner integral, the one with respect to r, and you say, well, given a typical value of theta in this range between 0 and pi over 2, what are the limits of the r variable? Okay, so there you're imagining a ray coming out from the origin at an angle theta. So between what values of the radius do you need to integrate over in order to cover the region r? Well, the region is only between the circles of radius a and b. So you need to integrate r between a and b. Okay? You don't want to integrate r over any lower values because that would pick up points inside the inner circle. And you don't want to integrate over r for any values greater than b because that would pick up points outside the larger circle. You know? So in line 192, there the transformation is complete. We've replaced the old function with its description in terms of the new coordinates. We described the region with limits of integration in terms of the new coordinates, and we've replaced the dx dy with r dr d theta. And there's a couple of steps skipped out then, but the integration happens easily enough now. The integral of 1 over r is, of course, the logarithm of r. When you evaluate that at b and a, you get the logarithm of b minus the logarithm of a, but you can bring those together as the logarithm of the quotient, b over a, using properties of logarithms. And then you're integrating this logarithm b over a with respect to theta between 0 and pi over 2. But then the thing you're integrating, the logarithm of b over a, that doesn't have any dependence on theta. So it just integrates, so it's just a constant as far as theta is concerned. So it just integrates to theta times logarithm b over a, and then evaluating that at 0 and pi over 2 gives you the final answer of pi over 2 times the logarithm of b over a. Okay, so if we had tried to do the original integral, you know, sticking completely within the Cartesian coordinate system of x and y, we wouldn't, you know, it would have been, we would have had to use very complicated formulae. Even describing the region, you're going to start to have to use square roots to describe, you know, what the y coordinate is given the typical x coordinate. So it would be a lot more awkward to do this integral solely with Cartesian coordinates. And that's because everything about the integral is talking about circles. Okay, 1 over the square of the radius term, and then the region itself is trapped between two circles. Okay, so it's a good example of the utility of changing coordinates. Okay, it allows you to carry out the integral. So before we go on to look at some more examples, just to look at the picture in general, you can scale this up to any number of dimensions. So if you're integrating a function of n variables, so f of x1 up to xn, with respect to, say, the normal Euclidean basis x1 up to xn of Rn, you'd be integrating over some sub-region of Rn, sub-volume of Rn, R, and then you could translate that integral into a new coordinate system. Okay, so you'd need a new system of coordinates u1 up to un. You'd replace, so here, I mean, it becomes just lots of dots and lots of indices in the notation. So you're evaluating f. So each xi you're replacing with its expression in terms of u1 up to un. So all these get substituted in. Then you have the new differentials, du1, du2, etc., up to dun. And then you also have the absolute value of the Jacobian of the transformation. So that's looking at that material that we have in the notes. So I'm going to supply a few more examples here on the overhead, and a bit of an explanation of why this Jacobian is cropping up there in the new integral, and a little bit on its meaning. Okay, so we'll do that. So first of all, just to recall, okay, we made use of the Jacobian of the transformation from Cartesian coordinates to polar coordinates. coordinates. I'll just remind you of how that went. See, the relationship between these two coordinate systems is, of course, x is r cosine theta and y is r sine theta. So, example here, here's a point with coordinates x, y, but r is the length of the hypotenuse, theta is this length here. So the x and y are related to r and theta through this cosine and sine functions. And by definition, the Jacobian is the matrix of partial derivatives by dx dr and dx d theta on the first row. So the first old variable indexes the first row, then the second old variable y indexes the second row. So dy dr dy theta. So that gives us a little 2 by 2 matrix, 2 by 2 determinant involving r's and cosines, etc. So dx dr, so it's cosine theta there, dx d theta, it's minus r sine theta. Dy dr, so it's sine theta, and theta r cosine. And you multiply out this determinant, and you get r times cosine squared theta plus sine squared theta, which is equal to r. Now, what this Jacobian determinant means, so this is what fed into the translation of the integral in the previous example. The geometric meaning or interpretation of the Jacobian is that it's a scaling factor occurring in the area element dx dy. So dx dy is a little change in x, think of it, times a little change in y. So that's a little bit of area in the domain of the function. Factor occurring in the area element dx dy when translated to the new coordinates. And you can get a feeling for this with the diagram. So the Jacobian, it's a scaling, some kind of scaling factor, let's put that in, which occurs in the old coordinate system. When you look at it in the new coordinate system, the area element is r dr d. We're not going to go into this in a huge amount of detail, but I do want to get across a feeling for why there is this funny thing going on with area elements. Okay? So we'll draw a picture of the plane. This picture of R2. Now, if we talk in terms of the Cartesian coordinates, if we make a little change in so we're interested in the, I'll just draw. What kind of area is covered when you change the x coordinate and change the y coordinate? Well, if you change x a little bit and change y a little bit, what you get is a little square or a little rectangle. Okay? Just got dx and dy. Now this kind of picture shows you starting with the values x and y equals 0 and changing them a little bit. Changing x to something small and positive, changing y to something small and positive. And that describes a little the space in the domain that's covered by those changes is a little rectangle. And no matter what starting value you use, so suppose x and y have original values which place you out here in the R2 plane. If you change x and y by a similar amount, then they cover, well, exactly the same amount of area. So no matter where you are in the plane, if you change x a little bit, change y a little bit, you cover a little bit of area. And that area doesn't change depending on where you were in the plane before you made the changes. Well, polar coordinates work very differently. So that's the xy Cartesian coordinates in black. But I'll put the polar coordinates in red. So the polar coordinates are r and theta. But they work quite differently. If we start off at the origin and imagine changing the radius a bit and changing the polar angle theta a bit, well, if we were starting off at the origin, changing the radius would move us out a bit along here. Let's say we change the angle between these two values. So we describe a little bit of area there. Okay. Starting at the origin, changing the radius by a little bit, and changing the angle by a little bit. However, if you started off, say, at some value down here, and you change the angle by a little bit, that would move you on an arc here. You change the radius by the same amount. So the increase in radius I'll do is going to be the same, roughly. So this area here is the same change. You assume it's the same change in the value of the radius and the same change in the value of the angle. But because it's located further from the origin, it actually describes a much bigger area. Okay. And if you were going to go to extremes, continue with this picture out, if you make the changes out here, the area is even bigger. So for polar coordinates are different. If you vary the radius a little bit and vary the polar angle, the amount of area you to cover depends on where you are to begin with. Okay? If you're located at the origin, the small change in r and the small change in theta covers a small area. However, if you're 1,000,000 miles away from the origin, okay, the change in radius is still changing it by an inch, say, whatever that is. But if you're changing the angle by the same angle, well, if you're millions of miles away from the origin where these radius rays come out of, changing the angle moves you across a huge distance. Yeah. If I move across an angle here, within the room, I'm only moving a few feet. But if I bring the location out to a few miles away from me swinging my arm like that through the same angle covers a huge area, hundreds of square miles. We're talking about a point quite a long distance away from it. Okay? So the area covered by dr theta, changes in r and theta, depends on the location, whereas it doesn't for Cartesian coordinates. Okay? No matter what starting point you go from, a little change in x and a little change in y always covers the same amount of area. So the precise dependence is given by the absolute value of the Jacobian times dr d. Okay, so in the case of polar coordinates, it's r dr d. So when we're doing these two-dimensional integrals, and we're integrating over areas in the plane, in the domain of the functions for two variables, when we're moving to a new system of coordinates, we have to take account of how those coordinates, how they describe area elements, is the phrase that's used. So when we change the coordinates a little bit, introduce a small variation in the coordinates, what kind of area is covered by this change? Okay, so let's look at a three-dimensional example. so now we're going to look at a three-dimensional example, which is going to be an integral, not over a region in the plane, but over a piece of volume in R3, in three-dimensional space. And we're going to describe it in a way that's suitable for the cylindrical coordinates. Okay, so we're going to make use here of the Jacobian. We're going to ask for the original integral with respect to the Cartesian coordinates, and then make use of the Jacobian of the transformation from Cartesian to cylindrical. So this is a 3D example. So x, y, z. What we want to do is we want to compute an integral here over this kind of, imagine this kind of bell-shaped volume here. We'll consider the region R using region in a general sense, so this is a three-dimensional region, and this is bounded by the z equals 0 plane. So the z equals 0 plane is the xy ground plane, if you like, the x and y coordinates spanning the ground, z being the vertical axis coming up off the ground. So this bell-shaped volume is resting on the ground. The ground is the bottom surface of it. And the side surface, which comes up from the base circle up to the point up there, and bounded by the paraboloid, it's called. Paraboloid is a three-dimensional analog of a parabola. And this is rho squared equals 9 minus z. Now remember, in the cylindrical coordinate system, rho, Greek letter rho, that represented the length of the projected radius of the point. So a point in 3 dimensions has a radius, which is the line connecting it to the origin. And rho is the projected radius. When you project the point vertically down onto the xy plane, or vertically up, the point is below the z equals 0 plane. And rho then is the length of the projected radius. That's part of the cylindrical coordinate system. Theta is this polar type angle here. The other aspect of the cylindrical coordinate system rho is the radius is 0, or the kind of cross-sectional radius is 0 when z is equal to 9. So this point at the top is where z is equal to 9. And what we want to do with this region is we want to compute the integral I, where I is originally described, so it's a triple integral now, integrating rho squared dx, dy, dz. So we're integrating rho squared dx, dy, dz. So rho squared could be some kind of like measure of the density of this region. So the density depends on the kind of cross-sectional distance from the z-axis. So yeah, for any point in 3 dimensions, rho, you can also think of rho as being the cross-sectional distance of that point from the z-axis, so the horizontal distance of the point back to the z-axis. Now, this integral needs transformation to cylindrical coordinates. Okay, because, well, the function we're integrating is the square of rho. That's one of the variables occurring in cylindrical coordinates. And the region we're integrating, well, one of the surfaces defining the boundary of the region is itself given as an equation of cylindrical coordinates, rho and z. Okay. So we'll need the Jacobian d x, y, z, d rho theta z. So for cylindrical equations, for cylindrical coordinates, the transformation equations between the two coordinate systems are, well, x was rho cosine theta, y was rho sine theta, and well, you've got this third trivial equation, z equals z, because we're using the same z coordinate in both coordinate systems. So these equations tell you what the old coordinates x, y, and z are in terms of the new coordinates rho, theta, and z. So the Jacobian determinant then dx, y, z, d rho, theta, z. Well, this is going to be a 3 by 3 determinant now. And look back on the notes. So the first row is going to be all the derivatives of the x variable with respect to rho, theta, and z in that order. So dx d rho is cosine theta. Dx d theta is minus rho sine theta. And dx dz is 0, because there is no z in x. It's small. The second row is indexed by y, so it's dy d rho, dy d theta, dy dz. The dy d rho is sine theta. Dy d theta is rho cosine theta. And dy dz is 0 again, since no z in changing z does not change the y coordinate of the point, just moves the point vertically up and down. Points x and y coordinates stay the same. And then the third row is indexed by z, so it's dz d rho, dz d theta, dz dz. Of course, there's no rho and theta are independent of z, and dz dz is just 1. If you're at any point in space, changing the rho and changing the theta does not alter the height of the point. It keeps the point at the same height, so that's why there's two derivatives. So clearly, you should expand this determinant along the third row, or down the third column, so that's where all the zeros are. And the determinant comes out as rho cosine squared theta plus sine squared theta, which will be equal to rho. So the Jacobian of the transformation from Cartesian into cylindrical coordinates as well. So we can put that to our use then in performing this integral I. So let's look at the various parts of I. I is going to be a triple integral over the region. Now we're integrating rho squared, but then we have the absolute value of the Jacobian, which is another rho, then d rho d theta dz. And we can put the d rho d theta dz down in any particular order, just to suit ourselves, really, to whichever one makes it easier to describe the region. Okay, so we've now looked at the three-dimensional region. Just about put them both there on the page. So we need to start filling in. So I put my integral signs far apart so I can fit in the limits of integration. So now you work from the outside in. So you look at your three-dimensional volume, and you say to yourself, well, so between what z values is the region in question? So bounded below by the xy plane, which is z equals 0, and it just goes up as far, that top point of it is at z equals 9. Okay. So the z variable we integrate between 0 and 9. Okay. Then we step into the next integral. Now, the outer z integral, that supplies a z value to the two inner integrals. So the theta integral, we'll imagine that we've got a typical value of z in the range 0 to 9. So that means we're at a typical height. Now when you're at a typical height, the region you need to describe is this kind of circular cross-section of the bell-shaped valve, okay? Because you're at a particular height, z, that's been supplied by the outer integral. So between what values of the angle theta do you need to integrate? Well, you need to integrate all the way around this cross-sectional disk through the valve. So you need to integrate around all angles, 0 to 2 pi. And then you've got a z. Then coming to the rho integral, you've got a z height. You've got a particular angle. So there you're talking about you've got a radial ray. How much of the radial ray do you want to integrate along? Well, just from the core z equals 0, the core z-axis, just out along the disk until you reach the boundary of the circular disk cross-section. What would that be? That would be, well, this is a paraboloid, which is defined by rho squared equals 9 minus z. So the upper limit for rho should be the square root of 9 minus z. Okay. So this is our integral I, and now it's been completely transformed from the Cartesian coordinates x, y, z into this new cylindrical coordinates. There's no mention of x, y. Well, there is mention of z because z occurs in the cylindrical coordinate system as well. There's no mention of x and y, and everything is expressed in terms of rho, theta, and z. And this is, we can carry this out now. So you do the integrals from the inside towards the outside. So you leave the outer two integrals alone. And you're integrating, well, we'll be integrating rho cubed. So that's going to integrate to rho to the power of 4 over 4. And we need to evaluate that at 0 and the square root of 9 minus z. So that's going to become, well, you can send the quarter out to the front using linearity. And then you're integrating 0 to 2 pi. You'll be integrating 9 minus z squared d z. So I don't think that's going to cause any problems. So the next integral to do is the theta integral, but the thing you're integrating doesn't have any thetas in it. So it will integrate to theta times this and then evaluate it at 0 and 2 pi. So that's going to give another factor of 2 pi. So finally, it'll come down to an integral like this. But this is just a quadratic in z. Easily integrate that. You do the evaluations and 2 pi over 4. And integrating this is going to be 81z. Minus say 2 over 2 z squared. And then you get a plus z squared, which will integrate to z. Integrating that 0 Okay, and that'll have, you know, whatever value it has. It's just a matter now of evaluating these all at evaluating those all. So that's an example of doing an integral of a function of 3 variables, integrating over a subregion of R3, so a subvolume, and integrating a function which is defined in terms of the cylindrical coordinates. So I'll give another 3D example. And this one is this one talks about spheres, so it's, I guess it's going to need spherical coordinates. This one asks us to find the mass of a sphere of radius A, speaking generally, radius A, whose density is inversely proportional to the square of the distance, square of the radial distance. So, i.e., that means the density D will be given by, so this kind of function. So D as a function of the coordinates x, y, z, the density would be, so it's going to be proportional to the, inversely proportional to the square of the radial distance. So the square of the radial distance is x squared plus y squared plus z squared. Now it's proportional, there's going to be some fixed constant k there. It being proportional to the inverse square of the radial distance is quite important. That's how the force of gravity works. Strength of the gravitational force is inversely proportional to the square of the radius. So it's an important concept. So we could set up this integral then. We could set this up in Cartesian coordinates, and then make the transformation into polar coordinates. Now the general principle is that mass, you get the mass by integrating over the region, integrating the density function. And that's the general principle. Density is mass per unit volume. If you add up all the density that there is inside the region, you get the mass of the whole region. Now this is a sphere of radius A, so this mass is going to be the triple integral over the sphere, radius A. Just describing that by name for the moment. Integrating the density function, so the density function is k over the sum of squares times dx dy dz. Okay, now there's lots about this integral that says we shouldn't try and just stay within the Cartesian coordinate system, okay, because the region that we're integrating over, sphere of radius A, it's going to be a lot easier to describe that using spherical coordinates. And the function we're integrating as well is very spherical. Okay. So for this, we'll need the Jacobian of the transformation from Cartesian into spherical polar coordinates. So those are spherical polar coordinates, or just spherical coordinates. Remind you, the spherical coordinates were x, y, z. So you have a point with coordinates, Cartesian coordinates x, y, z. R is simply the radial distance. Theta is this angle of the projection of the radius down onto the xy plane with the positive x-axis. So theta has its usual meaning. Phi is this angle here, zenith angle. The angle of the radius down from the vertical direction in the positive z-axis. The transformation equations which you'll need, I won't finish this example, but I'll set it up for you. You can look at it in the tutorials. Transformation equations, this is just reminding you what they were, was x equals, yeah, so this rho term is this projected radius term is r sine phi. So you get that multiplied by cosine theta for x, r sine phi times sine theta for y. And then z is a bit easier. Z is just r cosine phi. So we'll leave this as an exercise to find the Jacobian. Perform the transformation into spherical coordinates, and then you can figure out the limits to describe the sphere of radius A. The limits and the variables are theta and phi, and then evaluate it. So you should end up with a number for the mass. Of course, the number will depend on the big general here about the radius of the radius. Okay, that's good. As usual, I'll put scans of all these pages up in the comments to the lecture recording.